Welcome to the Sophistic online documentation. In this video of the Composite Bridge tutorial, we show how to do the ultimate limit state design checks for the main girders of the composite bridge. For this purpose, insert the task Composite Bridge Design Checks and open it. We start with the tab for the general settings. As you can see, the task works with design elements. In the table for the design element selection, you have a list containing all design elements of type comp in the system. Recall that we explicitly defined such a design element for the left main girder. For the check, you can either select all design elements in the list or manually select just some of them. Next, you select the checks to be done. The task offers cross-section resistance in the ultimate limit state, stress limitation in the serviceability limit state, drag width limitation, here the check of the minimum reinforcement and the check of the drag width due to direct loading. Furthermore, it offers the possibility to determine longitudinal shear forces for the design of the shear connection and stress ranges for the fatigue design checks. Note that the settings for the individual checks are done in the corresponding tabs. Please note that the results of the task will be stored under a load case number. The default is that these results can be found in load case numbers starting from 200,000 upwards. Note that you can also modify this value. Note also that in the General tab you have several options to modify the printout of the task. In the first step, we will focus here on the cross-section resistance in the ultimate limit state. By requesting the design check, the content of the corresponding tab is activated. Now let's start with the ultimate limit state cross-section resistance. First, we select the design load cases to be checked. Remember that we have created them previously using the task superpositions for combination rules. Note that in this tab only the design load cases for the design element results for the ultimate limit state combinations are shown. For the rather simple system, in this tutorial example, I would claim that it is sufficient to focus on the design load cases superposed for maximum and minimum bending moment My and maximum and minimum shear force we set. So I select those from the list. Remember that we have created two sets of combinations, one for the time at traffic opening with minimum creep and shrinkage, and one for the time end of life cycle with maximum creep and shrinkage in the system. We select load cases from both sets here. Note that the design check results for each of the load cases will be stored in a load case with number of the original load case plus the offset given below the load case table. Furthermore, an envelope of the results of all calculated load cases will be stored under the given number. There you can find, for example, the maximum of the stress in a material or a stress point over all calculated load cases. Okay, now let's go to the design checks. Here we provide several options how to do the checks for the structural steel part. Please recall that how to do the design check depends on the classification of the cross-section, which describes how prone to local buckling effects is the structural steel section. Class 1 sections have the most rotation capacity and would even allow for the development of several plastic joints in the structure and a corresponding distribution of the internal forces in the structure. Note that design concepts of a bearing capacity of the whole structural system with several plastic joints are not part of the scope of the bridge design checks presented in this tutorial. Sections of Class 2 do not allow for such plastic force redistributions in the system. Therefore, the internal forces in the structure are calculated elastic. However, the check of the bearing capacity of the cross-section may be done based on plastic stress distributions. When I talk about plastic design checks in this tutorial, I refer to this design concept. Sections of Class 3 are more slender and would buckle before reaching the full plastic bearing capacity. Here the checks are done based on the elastic stresses in the section. Sections of Class 4 are even more slender and might buckle before reaching the elastic bearing capacity. Here local buckling effects have to be considered by additional measures. I will give a short summary how Sophistic does the design checks for the different section classes. We will start with the plastic check for section class 1 or 2. The classification is done on the full plastic stress distribution, here depicted once for a positive bending moment and once for a negative bending moment. If the section cannot be classified accordingly, we have to go for an elastic check. If the section can be classified in section class 1 or 2, we can proceed and have to check whether interaction between bending and shear has to be considered. If the acting shear force is smaller than 50% of the shear bearing capacity, interaction can be neglected and the check is done by comparing acting bending moment against the full plastic resistance. If the interaction between bending and shear has to be taken into account, this is done by calculating the plastic bending capacity with a reduced strength of the web as depicted here in this sketch. Next, we will take a look at the elastic check. Here we provide two options which differ in the way how the interaction between bending and shear is treated and how local buckling effects are taken into account for class 4 sections. In the first option, the interaction between bending and shear is done based on von Mises stresses for section class 3 and for sections of class 4, or if shear buckling is relevant, by its generalization by the reduced stress method, where the effects of local buckling due to compression or shear stresses are taken into account by the corresponding reduction factors. Note that the classification of the cross-section is done based on elastic stresses that are calculated considering the construction process, creep and shrinkage effects, and that the concrete should be treated as having no tensile strength, so being cracked if in tension. Okay, now let's take a look at the second option for the elastic check. This variant consists of two parts. The check of the interaction between bending and shear, which has to be considered if the utilization of the shear bearing capacity is above 50%. If this is the case, the check for the interaction is done based on the interaction formulas from the Eurocode. Second part of the check is the check of the axial stresses based on the elastic stress distribution. In case of sections of class 4, the stresses are calculated based on the effective section according to section 4 of Eurocode 3, part 1.5. Okay, if both parts of the check are fulfilled, then the overall elastic check is fulfilled here. Now let's go back to the task. Here you can select whether the plastic resistance should be applied for the check, if the section can be classified accordingly, and if you want to do the elastic check using the reduced stress method and Van Mises stresses, or using effective cross sections and the interaction formula for the bending shear interaction. We will first keep the default and present the calculation with setting use plastic resistance if possible and use the reduced stress method. Before starting the calculation, a short note about the safety factors for the material. They can be set via the design state. There are several options. Automatic means that the safety factors will be set according to the type of the design load case. In this example, we have only load cases of type ULS fundamental combination. However, in general, there might also be load cases of the type ULS accidental combination or even a seismic combination requiring different safety factors. When using the automatic option, the safety factors for the check will be set for each type according to the default for the selected code, respectively national annex. By setting ULS fundamental combination, accidental combination, or seismic combination, you can explicitly request the safety factors for this type of ULS combination for all selected load cases. Note that these factors are then also shown informatively in the line below. Finally, you can also set the factors for the individual materials explicitly. Okay, we will go with the automatic option, run the task, and take a look at the report. In the task definition, you get an overview of the design checks, the check design elements, and load cases. Then we start with the plastic check. For example, for the maximum MY load case 3029. Here you first get an overview table for every section. Along the design element, you get the cross-section ID, acting shear force, full plastic shear resistance considering shear buckling, which gets decisive here, and the corresponding shear utilization. And then acting bending moment, bending resistance, the fully plastic one first, and then in the next column, the bending resistance for the case that the shear utilization is above 50%, so with reduced strength of the web. However, this is not the case here, so we get the same values as before. And finally, then the utilization of the bending resistance, and most important, also the cross-section class, which shows if the plastic check is applicable. Here for this load case superposed for maximum MY, this is the case. We have section class 1 all over the whole length of the girder. Plastic check is applicable and as you can see also fulfilled. The table is followed by an overview plot that visualizes the values from the table along the design element, respectively girder. Once again, acting shear force, shear resistance, and same for the bending moment. And to check the cross-section classification, we have the position of the neutral axis plotted against the contour of the girder and below the section class resulting from the fully plastic stress distribution. Then comes the overview table for the elastic check. Here, once again, for each section along the girder, we get for each material in the section the stresses at the decisive position in the section, reduction factors for the axial and shear strength to consider local buckling via the reduced stress method, strength of the material, and finally the utilization and cross-section class determined from the elastic stress distribution. This is followed by an overview plot of the elastic check that that shows along the girder for each material type the decisive utilization. Finally, we get a table that sums up the plastic and elastic checks for the investigated load case. There we have for the sections along the girder, the plastic shear and bending utilization and cross-section loss from the plastic stress distribution, and the utilization from the decisive utilization from the elastic check, and the cross-section loss from the elastic stress distribution. For this load case, they are all fulfilled, and consequently the check is fulfilled. Let's check out the more interesting example, like a load case superposed for minimum bending moment My. Here you can see that section class 2 cannot be fulfilled at many sections along the girder, so a plastic check is not feasible, but the elastic check is fulfilled at all sections, so the overall check for the girder is still fulfilled, and the resulting cross-section class is free in most cases. In this way, we can go through all the load cases that have been selected for the check, and in the end we get a summary for all selected design elements. Here we have only one, and the selected load cases. Okay, now you might be interested how the utilization and the section class are determined in detail. To get this, you can request detailed output at selected positions. To get this, open the task, and there you can request detailed output at selected positions. In the corresponding table, you can add one or several lines. For your positions of interest, select the design element, the position of the section along the girder. Note that it is not required to write the exact position of an existing section. The program takes the section which is closest to the entered values. Here I take a section in the span at approximately 8 meters. You can request the detailed output for all selected load cases in this tab, or explicitly select one. We will take a look at load case 3029 here as an example, and we will start with the standard setting for the output depth. Later I will also explain the other options for this column. Having the selection done, we rerun the task and take a look at the report. For the selected load case, an additional section for the detailed output has appeared. Here we first get information about the plastic check, the position of the plastic center in the cross-section, and the corresponding plastic stress distribution, including the summary of tension and compression forces that constitute the plastic bending resistance. Furthermore, the details about the plastic cross-section classification. Note that you can check out the names of the thin-walled elements in the plot of the cross-section above. Next, there is a table showing the elements recognized as webs that constitute the shear resistance. Note that you also get information about the reduction factor for shear buckling here. Next, we get to the part related to the elastic check. The design load cases selected in the task have been created by a superposition. In order to correctly consider the construction process in the elastic stress calculation, the individual load cases that contribute to the design load case are traced. In the table subload cases of the design load case, you can check out the individual contributions from the construction process and the live loads. Next, we get a table that shows the redistribution of forces between the materials of the cross-section due to primary effects of creep and shrinkage. Based on these contributions, the axial and shear stresses in the cross-section are calculated, and you can check them in the plots. Based on these stresses, the section is classified, and you get the information about the C2T check and the resulting section class in the next table. Note here that we explicitly deselected the elements of the top flange for the C2T check because they are directly attached to the concrete slab and therefore not prone to buckling. Remember that we did this already when defining the cross-section. The final table of the detailed output shows for each structural steel element in the cross-section where the decisive utilization occurs and how it is determined. Now, you might still be skeptical if the construction process has really been considered in the stress calculation. To check this out, you can go back to the task and select a more extensive output depth for the detail. So we select here, including the development of stresses. We run the task, go to the report, and you can see that additional plots have been added now. We can go now through the individual subload cases of the design load case and see how the stresses develop during the construction process and when adding the live load. First, we have the pure structural steel section active. Here on the right axial stress, the left axial stress, on the right shear stress. Now the concrete hardens. Further loads get applied on the now full composite section. And then we get to the live loads. And please note that the contributions of primary effects from creep and shrinkage are considered at the very end of the stress calculation, because just at this final state we can determine if the concrete in the section is finally cracked. Then the stress redistribution between steel and concrete has to vanish, or if the concrete is uncracked, as is the case here, the redistribution has to be considered, and you can see here, concrete creeps and shrinks, and consequently, for example, the compression stress in the upper flange increases. Okay, so we have checked the stress development and seen how the stresses for the final check have been determined. And that's it so far about the first option for the elastic check, but maybe you prefer to use the second option, so the bending shear interaction by interaction formula and class 4 section via the effective cross sections. To check this out, we once again go to the task and set the corresponding option. Furthermore, I set the position of the detailed output to 6 meters here and select load case 3030 because I already know that at this position there is something I would like to show you. Okay, then we run the task and open the report. The elastic checks remain the same, but in the elastic checks you can see the difference now. It starts by checking the interaction between bending and shear. For each section along the girder, we have the acting shear force and the shear resistance, giving the shear utilization. At most sections, the shear utilization is below 50%, so we don't have to consider the interaction between bending and shear there, but close to the inner support, we have to check the interaction, which is done by the corresponding formula from the Eurocode. Input values are the shear utilization, full plastic bending moment, and the plastic bending moment considering only the contribution of the flanges. We can see now that the check for the bending shear interaction is also fulfilled at the inner support. Okay, so the interaction check we have done. Next we check the axial stresses in the section. Here we have for each section along the girder, for each material in the section, the axial stresses, strength, resulting utilization, and the cross-section class. Finally, we get a plot that gives an overview of the utilizations from the tables along the girder And finally, a table that once again sums up the utilizations from the plastic and elastic check. You see that we have some sections of class 4 where we expect to see the use of an effective cross-section. We will check this out in the detailed information for the section at approximately 6 meters. Let's go step by step. We will skip the detailed information for the plastic check. I have shown them previously. But now we also get some information for the bending shear interaction of the elastic check. Remember that one parameter in the interaction formula was the relation between fully plastic bending resistance and the plastic bending resistance calculated only for the flanges. Now in the detail, you can check out the stress distribution related to these two values. Next, we have once again the summary of the sub-load cases contained in the design load case and the primary effects of creep and shrinkage, and then the development of the resulting stresses. You can see here how the effective cross-section is applied. And also check out in the following tables how the effective widths are calculated and applied. I would like to add a final note. Please be aware that the plastic check according Eurocode 4 section 6.2 and also the bending shear interaction from Eurocode 3 part 1.5 section 7.1 are designed for systems with predominantly uniaxial bending, focusing purely on shear force reset and bending moment in Y. So for systems where biaxial bending or torsion is significant, it might be more appropriate to use the elastic check based on Vermees stresses, respectively the reduced stress method. The program will therefore trigger a warning in the plastic design check when it detects significant bending in cross direction. However, the decision if this is really an issue for the system and which check should be applied has to be made by the user. That's it so far about the ultimate limit state design checks. In the next video, we will proceed with the checks in the serviceability limit state. See you soon.